Hi everyone. In this part of the lecture, we are going to take a look at the method that we can use to improve the efficiency of the Rankine cycle. The method that we are going to use here would be called the regenerative scheme. Now, before moving into the details of the regenerative scheme, let's have a look at the cycle of the Rankine cycle on TS diagram first. This is the shape of the Rankine cycle on TS diagram. You can see that if we want to improve by using the regenerative scheme, as we have done in the Brayton cycle, we have to use the turbine exhaust here to exchange heat with the pump outlet here. Okay. Now you can see from this diagram, obviously, that the temperature at the turbine exhaust or T4 is less than the temperature of the pump exit at T2. Okay, so you can see that you cannot recover the heat from the turbine exhaust here to the pump exit here, okay, because the temperature is lower. So to use a regenerative scheme, you have to withdraw the steam at a higher temperature instead of using the steam at the final exhaust temperature here. What you can do is that you have to withdraw the steam at some point, okay, at some intermediate point, at higher temperature or at higher pressure. You have to withdraw some amount of steam out from the turbine, okay, and use this amount of steam, okay, use this amount of steam to transfer heat or to preheat the water at the pump exit. Okay, so in this case, the water that enter the boiler would be at a higher temperature, or that would be the regenerative scheme that we are looking for. Now the drawback of this method is that when you withdraw some amount of steam from the turbine, it means that the steam that would be expand further to the final exhaust pressure would be lower. For example, if the total amount of steam entering the turbine is 1 or 100% full fraction, okay, if you withdraw some amount of steam out, for example with fraction y, you can see that the expansion of the steam from your withdrawal point to the final exhaust point would be reduced to just 1 minus y. Okay, you can see that the amount of steam would be reduced in this part. So it means that by using the regenerative scheme as we have talked about here, it means that W net would be reduced. Okay, W net would be reduced. This is what we have to pay for. Okay, we reduce W net in order to save amount of heat requirement, to save Q in, okay, to save amount of heat requirement in the boiler, okay, and we hope that the net result would be we can increase the thermal efficiency of the overall cycle. Okay, so this is the regenerative scheme in the Rankine cycle. All right. Now, the regenerative scheme in the Rankine cycle here, we can do that in two different ways. The first way is that we can use open feed water heater. Okay, the first method here, open feed water heater. In this method here, there's extract steam. The extract steam here would be used to mix with the water from the pump directly. Okay, they would be mixed, physically mixed. Okay, so extract steam with the high temperature would be mixed with the liquid from the pump at lower temperature, and this can increase the temperature of the boiler feed water. So we call this scheme open feed water heater. In the other method, we can use closed feed water heater. Closed feed water is that we can use extract steam that we get from the turbine. We can use it to exchange the heat with the condensate or the water from the pump exit by using a heat exchanger. Use a heat exchanger. So it means that the extracted steam and the water from the pump will not be mixed. Okay, so in this scheme we call the closed feed water heater. Okay, let's talk about the details of the open feed water heater first. Okay, in the open feed water heater, you can see that we have some more equipment that we have to install in the Rankine cycle. First of all, we have a mixer here. This is a mixing chamber, open feed water heater. Okay, you can see that in our turbine would be called extraction turbine. Extraction turbine is the turbine that we have more than one outlet. Okay, so you can see that in this kind of turbine you have steam withdrawn or you have steam extract at some intermediate point. Okay, so you have two outlets. You have outlet at number 6 at some intermediate pressure, and you have another outlet at number 7, which is the final exhaust pressure here. Okay, and you have one inlet here. The main inlet is at number 5. Okay, so with the steam that you extract, okay, we assume that I use the amount or the fraction of Y. This amount or this fraction of Y will be mixed with the water from the pump exit here. Okay, and then after mixing, the temperature would be increased to the point number 3, and then it will be pumped to the final pressure, to the higher pressure, before entering the boiler. Okay, so you can see that in the regenerative scheme here, we are operating our Rankine cycle with 3 different pressure level. Okay, if you look at the TS diagram on your right hand side here, you can see that we have high pressure here. We have intermediate pressure, okay, here, and we have low pressure here. Okay, we have high, intermediate pressure and low pressure here. Right, then you can see that the flow rate of the steam entering the turbine is 1. So you can see that in the boiler we have the fraction of 1. After the steam expands through the turbine from high pressure to intermediate pressure, you can see that the flow of steam through this part of the turbine is still 1. But after that, when you withdraw some amount of steam out at number 6, you withdraw with the fraction of Y. The remaining amount of the steam would be 1 minus Y. This remaining amount of steam will be expanded further from 6 to 7. Okay, so you can see that the amount of steam that would be condensed in the condenser would be just 1 minus Y as well. 1 minus Y. This is the condenser. 7, 1, 7 to 1 here. This is your condenser. Okay, after that, when you condense all the vapor into the liquid, you pump it to the pump. You can pump it to the from low pressure to intermediate pressure. This fraction is also 1 minus y. Okay, after that, you can see we will mix them together. We mix the water from the pump exit with the steam, which is at number 6, that we extract at intermediate pressure level. We mix them together, we get the final mixture at number 3. Okay, we get the final mixture at number 3. So you can see that we normally mix it in order to achieve the liquid at sat liquid. So number 3 would be at sat liquid. Okay, we mix number 6 and number 2 to obtain number 3. Number 3 is sat liquid. And then finally we pump the mixture here from number 3 to number 4. This one would be the fraction of 1 again. Okay, the full fraction, and then it will enter the boiler at point number 4. Okay, and then continue the cycle. Okay, so this is how we do it in the regenerative Rankine cycle using open feed water heater. Okay, let me draw the fraction on the diagram here as well. You have the full fraction here, 1. You withdraw y here. Okay, the remaining part, 1 minus y, will come out from the final exhaust from the turbine through the condenser. It is also 1 minus y. Through the first pump, the flow rate is 1 minus y. Okay, and the outlet of the open feed water heater, the flow rate is 1. From the pump number 2, flow rate is also 1 as well. Okay, right. Now let's move on to the next type of the regenerative scheme in the Rankine cycle. It is called the closed feed water heater. Okay, with steam trap to condenser. Okay, now in this scheme we will have extraction turbine as in the previous scheme. Okay, the diagram would be shown like this. Okay, you can see that we have a turbine inlet at number 4. We have the extracted steam at number 5, and the final exhaust steam at number 6. Okay, 4, 5, and 6 here. Okay, now in this case, the extracted steam will not be mixed with the water directly as in the open scheme, open feed water scheme, but it will be used to exchange the heat with the water by using a heat exchanger. This is a heat exchanger. This heat exchanger is called the closed feed water heater. Closed feed water heater here. Okay, after exchanging heat with the water, okay, the steam will be condensed to the liquid, and then it will be flashed through a valve, and then go to the condenser again. This is the scheme that we are talking about, the closed feed water heater with steam trap. Okay, now let me draw the cycle on the TS diagram for you. You can see that I'm going to start with the extraction turbine. The extraction turbine, we have number 4 here. Okay, we have expansion, like this. Okay, we have expansion like this. Okay, so this is number 5, and the final exhaust is number 6. Okay, this is at high pressure, this is intermediate pressure, and this is at low pressure. Okay, and for the pump start at number 1 here. We will pump it to the highest pressure from number 1 to number 2. Okay, from number 1 to number 2 here, from the diagram here. And then you can see that we will use the steam that we extract from number 5. Okay, it will be used to transfer heat or exchange heat with the water. 5 will be transfer heat with number 2. 5 will come out at number 7. Okay, while the water from the pump, it will increase to number 3. 2 will increase to number 3 here. Okay, and after that, from number 3, it will enter the boiler. Okay, water here from number 3, it will enter the boiler, and then it will change to the sad liquid, and then going out from the boiler as superheated steam at number 4, like this. Okay, now for the extracted steam that you used to heat up the water, it came out of the heat exchanger at number 7. It will be flashed through a valve. So from the number 7, it will be number 8. When it is flashed through the valve, you can see that some amount of vapor will be generated. So from 7, okay, to 8, this process is what we call isenthalpic process. Isenthalpic, or someone used the process Joule-Thomson expansion or JT expansion, Joule-Thomson expansion. So in this expansion, it will flash through the valve. Temperature will be decreased, but entropy will be increased because this process is non-isentropic. Okay, so the part of this process would be from 7 to number 8 here. So this is how it flashed, okay, through the valve, 7 to 8. And then 8 and 6 will be mixed together and then condensed in the condenser. 6 will be condensed in the condenser, and 8 is also condensed in the condenser as well, and the result would be 1. Number 1 is the water from condenser. 8 and 6 are both condensed in the condenser, okay, to become sad liquid at number 1, and then it will circulate in the cycle again. Alright, now let me draw the fraction in each part of the cycle for you. You can see that the fraction here in the boiler, we have the full fraction 1. Okay, in the first part of the expansion, we also have the full fraction or 1. Okay, at the intermediate point, we withdraw steam with the fraction of y. Okay, in the final expansion, in the last part here, we have the flow rate of 1 minus y. Okay, this part here, we have from 6 to 8 here, we have 1 minus y as well. Okay, and from 7 to 8 is y fraction, from 8 to 1 is 1. Okay, 1 to 2 is 1 now. 2 to 3 is also 1. Okay, full fraction. Okay, so you can see that the fraction of the flow are not the same at some point in your regenerative scheme. Okay, some part you have the full flow, some part you have only y fraction, some part you have 1 minus y fraction. Okay, now let me draw the diagram of the heat transfer in the closed feedwater heater for you. In the closed feedwater heater, if you draw the temperature profile, okay, if you draw the temperature profile of heat transfer between the hot and the cold stream on the TQ diagram, okay, you will have the profile like this. Okay, you have cold stream changing temperature from 2 to 3. Okay, but for hot stream you have temperature changing from 5 to 7. Okay, 5 to 7. You can see that we have the latent heat, okay, from the steam. Okay, we use to increase the temperature of the water from 2 to 3. Okay, so the heat transfer from hot stream must be equal to the heat transfer from cold stream, or the amount would be equal to Q regen. Q regen here. Okay, all right then. So this is the closed feed water heater with steam trap to the condenser. The cycle will look like this one. We also have another scheme of the closed feed water heater as well. This is another scheme. In this scheme, we also use a heat exchanger, okay, which is a closed feed water heater as well. But the difference is that in this game, we will not use the valve, the flash valve, to flash the sad liquid, okay, to the low pressure. Okay, you can see that number 3 here is the same point, is the exit, okay, of the extracted steam from our closed feed water heater, number 3. You can see that number 3 here, you can see that it's still at high temperature. It has a potential to increase the temperature of the water. We should not use it to flash it down to the low temperature. It would be such a waste. In this case, instead of flashing down to low temperature, low pressure like this, we don't use this one. Okay, we will pump it back to the higher pressure. From intermediate pressure, we pump it to the high pressure, and we use it to mix with the water from the closed feed water heater again. Okay, so in this scheme, it looks like we use a combination of the closed feed water heater scheme and the open feed water heater scheme together, okay, to make the maximum use of the heat that we have from the extracted steam. Okay, so you can see that the equipment that we have a heat exchanger, and we also have a mixing chamber. Okay, both heat exchanger and the mixing chamber here. Okay, now the scheme looks like the closed feed water heater, except in this part. Okay, except in this part. I'm going to zoom in to into this part. Okay, zoom into this part. You can see that the water from the closed feed water heater, or number 3 here. The water from closed feed water heater, or number 3, is here. Okay, we will pump it up. Okay, first to number 4. Okay, pump it up to number 4. So this is at intermediate pressure. This is at high pressure. Okay, so we pump it up from intermediate pressure to high pressure, and then we will mix this water with the water that we get from the closed feed water heater. We mix it with number 9. So 9, we mix it with 4. The result would be number 5. Okay, 9 mixed with 4, here you get the result at number 5. Okay, so you can see that you can increase the temperature of the water further from 9 to 5. T5 would be higher than T9. Okay, and the temperature of the water which enter the boiler would be at number 5. Okay, number 5 here. So you can see that you increase the temperature, the boiler feed water temperature, from T2 to T9 and to T5. Okay, from T2 to T9 and to T5. Okay, so in this way you can see that you can save the fuel consumption in the boiler. So Q in will be reduced further. Okay, in this case. Alright, so in this case here, let me draw the fraction for you. Okay, you can see that in the boiler you have full fraction 1. In the expansion, in the first part, it would be 1 as well. You extract some amount of steam at number 7, it would be with fraction y. Okay, the latter part of the turbine, it would be expand with fraction of 1 minus y. Okay, the flow rate through the condenser would be 1 minus y. Okay, the flow rate through the pump, the first pump here, would be 1 minus y as well. Okay, and from 2 to 9 it would be 1 minus y. Okay, after that, when you mix 9 with 5, from 5 to 6 it would be 1 now. Okay, from 5 to 6, flow rate would be 1. Okay, from 5 to 6, flow rate would be 1. Okay, so you mix y here with 1 minus y here. Okay, and number 5, it would be 1 again. Okay, so this is the scheme of closed feed water heater with pump back to the boiler pressure. Okay, all right. The heat transfer in the closed feed water heater is also the same. You can draw the temperature profile on the TQ diagram as well. TQ diagram. Okay, you have heat exchange between the extract steam and the water. So heat exchange would be between extract steam and the water, which is from 3 to which is from 2 to to 9. Okay, 2 to 9. And the extracted steam would be from 7 to 3. To 3 here. Okay, so this is a temperature profile in the closed feed water heater in this case. The amount of heat transfer is also Q regen. Okay. Now you can see that we have 3 different types of the regenerative scheme in the Rankine cycle. Now I'm going to explain only the first one, the one with the open feed water heater. Open feed water heater here. Okay. The main thing is that you can see that we have to extract some amount of steam. So the amount of the extracted steam is a very important parameter that you have to know. Okay. Now you can calculate this fraction y here. Okay. The fraction y here, you can calculate that. Okay. By doing the energy balance around the open feed water heater. Open feed water heater. You can also do the mass balance around the feed water heater as well. Okay. Now let's talk about the mass balance first. You can see that from the feed water heater, open FWH, open feed water heater, you have extracted steam, which is number 6, with the fraction of y. Okay, you mix it with the water from pump, which is at number 2, with the fraction of 1 minus y. Okay, and you get the result would be at number 3, which is at full fraction. Okay, so you can write the mass balance in mass flowing in equal to mass flowing out. So you have M6 plus M2 equal to M3, but M3 here is at full fraction or 1. M3 would be equal to M5. Okay, M5 is the flow of the steam into the turbine. M3 equal to M5. Now you can write M2 in terms of M5. Okay, so M2 will be equal to M5 minus M6. Okay, and M6 here, okay, M6 here is y fraction of M5. M6 here equal to y M5. So you can rewrite the equation here. You can find out that M2 would be 1 minus y multiplied by M5 here. Okay, that would be your M2. So you can write the mass flow rate at any point in your Rankine cycle as a function of the y fraction and the flow rate, the total flow rate at M5. Okay, like this. From the energy balance as well, you can calculate the energy balance by taking the equation energy flowing in equal to energy flowing out. In the open feed water heater, we assume that it's adiabatic. So energy flowing in would be from the flow rate of the steam flowing in. Okay, so energy flowing in would be M6H6 plus M2H2 equal to M3H3. Okay, from the mass balance that we have derived, we found that M6 equal to y M5, like this. Okay, we have derived that M2 equal to 1 minus y M5, this one. Okay, and M3 is also equal to M5, like this. Now we can rearrange our equation to write it in terms of y as a function of the enthalpy. So you can write y as a function of enthalpy at point 2, 3, and 6. Y equal to H3 minus H2 divided by H6 minus H2. Okay, so it means that if you know the enthalpy value at point 2, 3, and 6, you can calculate the fraction of steam that you need to extract, okay, to be mixed with the water, and get the final result as the sat liquid, or the final result at number 3 that you want. Okay, so this is an useful equation that you can use to determine the fraction of the extracted steam. Now you don't need to remember this equation. You can just derive it from the mass and energy balance that I have shown you here. Okay, so if you just remember the equation, you may be able to make some mistake because the number of the point or the location around the open feedwater heater may not be 6, 2, and 3 like this. Okay, so it's better to understand and derive it from the mass balance and the energy balance. Okay.